We in the night sky, humanity's first glimpse at comets. Have you ever stood beneath a star-filled sky, only to catch a glimpse of something extraordinary? A glowing streak of light, arcing across the heavens like a divine brushstroke? That was no shooting star. That, my friend, was a comet. For thousands of years, these brilliant wanderers have captivated our imaginations. They arrive unannounced, blazing across the night with shimmering tails, stirring wonder, curiosity, and sometimes even fear. In ancient times, comets were seen as omens, mystical messengers of disaster, war, or great change. Civilizations wove them into myth. To early humans, comets didn't just light up the sky, they lit up the soul. But as science emerged from superstition, we began to ask deeper questions. What are comets made of? Where do they come from? Are they leftovers from the formation of the solar system? Could they have brought water, or even the building blocks of life, to Earth? It took centuries for us to move from fearful awe to fearless exploration. And over the last 50 years, we've made a giant leap. Thanks to brilliant minds, daring spacecraft, and relentless curiosity, we no longer have to wait for comets to visit us. We've started visiting them. This story is one of discovery. How humanity turned its gaze from the myths of the past to the realities of deep space. How we went from making wishes on comets to unlocking the secrets within them. From the first blurry images of icy travelers to dramatic landings on alien surfaces, this is the saga of how we learned to chase comets, and why what we found changed everything. The first steps: unlocking the mystery of Halley's comet. When you hear the word comet, there's a good chance the first one that comes to mind is Halley's comet. It's the comet that transformed comets from heavenly mysteries into scientific marvels. Unlike most celestial visitors, Halley's comet comes back regularly. Roughly every 75 years, this icy wanderer makes its return trip through the inner solar system, lighting up our skies and our imagination. In a single human lifetime, if you're lucky, you might catch it twice. But let's rewind a bit. Back in the 17th century, people saw comets as singular events, spectacles that came and went with no connection to each other. A comet in 1531 was considered entirely separate from the one in 1607 or 1682. That is, until Edmund Halley stepped into the picture. Halley, a brilliant English astronomer and a close friend of Isaac Newton, studied historical records of comet appearances and made a bold prediction. The comets observed in 1531, 1607, and 1682 were actually the same object, returning again and again. Using Newton's laws of motion and gravity, he charted its orbit and predicted its return in 1758. And when that icy traveler blazed back into view just as he said it would, though Halley himself had passed away by then, history was made. For the first time, humanity understood that comets followed predictable paths through space. Halley's name became forever tied to this cosmic clockwork. But Halley's comet wasn't done making history. In 1986, we decided it was time to say hello. At this point in time, space exploration was reaching new heights. NASA had already landed on the Moon, sent probes to Jupiter and Saturn, and deployed satellites that were transforming our view of the universe. But visiting a comet? That was a new frontier. As Halley's comet made its scheduled return in 1986, space agencies around the world scrambled to take advantage of the opportunity. What followed became known as the Halley Armada, a fleet of 5 spacecraft launched by 3 different countries, all racing toward the same cosmic target. Let's break down the team. The European Space Agency, ESA, sent Giotto, a daring little probe equipped with a color camera and cutting-edge instruments. The Soviet Union, in partnership with France, launched Vega 1 and Vega 2. These spacecraft had already completed a successful mission to Venus, and from Japan, 2 more missions, Sakigake and Suisei. These were Japan's first ventures into deep space, and although they were less complex than the others, they played a crucial role in gathering valuable magnetic and plasma data. Together, these missions formed an unprecedented global collaboration. Never before had so many countries united around a single cosmic event. As the spacecraft approached Halley, they encountered the challenges you'd expect when chasing a celestial object moving at 70 kilometers per second. Halley's orbit is not only highly elliptical, but also retrograde. It moves in the opposite direction of the planets around the Sun. It's also tilted 18 degrees off the plane of the solar system, which made the approach even trickier. But despite the odds, the fleet arrived. The first to send back images were the Soviet Vegas, which flew within 8,000 kilometers of the comet's nucleus. They took temperature readings, analyzed the coma, the glowing envelope of gas and dust around the nucleus, and provided vital data on Halley's surface composition. They also passed along their trajectory information to Giotto, which would follow a few days later and attempt something never done before: a high-speed flyby just 600 kilometers above a comet's surface. Scientists held their breath. As Giotto closed in on Halley, it snapped a series of photos. Images that, when stitched together, revealed an alien world like nothing we'd ever seen. The nucleus was a dark, irregular object, about 15 kilometers long, with towering jets erupting from its sunlit side. Here's the kicker. Halley's comet was darker than anyone expected. Way darker. So dark, in fact, that it reflected less sunlight than charcoal. This was a big deal because it shattered the long-standing dirty snowball model of comets. You see, scientists had once believed that comets were mostly made of ice, coated with a bit of rock and dust. But Giotto's images told a different story. Halley wasn't an icy snowball. It was more like a lumpy chunk of dusty rock, with patches of ice hidden beneath the surface. Even more fascinating was the behavior of its jets. Rather than outgassing evenly across the surface, Halley's activity came from just a few concentrated spots. Only about 10% of the surface seemed to be venting gas and dust into space. And yet, those vents were powerful enough to produce the iconic tail that stretches for millions of kilometers. The composition of the gas was equally eye-opening. Halley's tail contained not just water vapor, but carbon dioxide, methane, ammonia, and even hydrocarbons, compounds rich in carbon and hydrogen, the basic ingredients of life. That raised a big question. Could comets like Halley have seeded Earth with the raw materials for life? Another critical measurement was the deuterium to hydrogen ratio in Halley's water. This ratio acts like a fingerprint, allowing scientists to compare water from different sources. If the ratio in Halley matched Earth's, it could mean comets delivered water to our young planet. But as it turned out, Halley's ratio was very different, casting doubt on that theory. Still, the mission's accomplishments were enormous. Giotto survived the encounter, even though it was battered by dust particles that temporarily knocked it offline. Miraculously, contact was reestablished, and the data made it home. From 5 spacecraft, dozens of instruments, and 1 dazzling comet, we gained a treasure trove of new knowledge. We learned that comets are not gentle snowballs, but dark, rugged relics of the solar system's past. We saw firsthand that their activity is wild and uneven. And we gathered clues, still being studied today, about their role in shaping planets, oceans, and perhaps even life. Halley's comet was no longer just a bright streak in the sky. It had become a laboratory, a time capsule, a world unto itself. And the best part? It'll be back. Halley's next visit is scheduled for 2061. So mark your calendars, because the next time it lights up our skies, we won't just be watching. We'll be ready, smarter, better equipped, and more curious than ever. Because Halley didn't just change our understanding of comets. It opened the door to everything that came after. Cosmic collision, when a comet smashed into Jupiter. In the summer of 1994, something happened in the solar system that no human had ever witnessed before. A comet, torn into pieces by gravity, slammed into a planet. And not just any planet, Jupiter, the largest of them all. For once, we didn't just discover the aftermath of a cosmic collision long after it happened. We watched it unfold in real time. The story began a year earlier, in 1993, when a team of astronomers led by Carolyn and Eugene Shoemaker, along with David Levy, spotted a strange object through their telescope. What they found wasn't a single comet, but a broken string of fragments, like beads on a necklace stretched across the sky. It didn't take long to realize that this fragmented object had once been whole, and that its destruction was likely caused by a close brush with Jupiter's immense gravitational pull. Now, those pieces were on a collision course, falling back toward the very planet that had shattered them. For days in mid-July 1994, astronomers around the world turned their eyes toward Jupiter. The impacts began just beyond the planet's limb, out of sight from Earth-based telescopes. But soon, Jupiter's rotation brought the scene into view, and what we saw was unlike anything we had imagined. Massive dark scars bloomed in Jupiter's atmosphere, bruises left by high-speed collisions that tore through its upper cloud layers. The plumes from each strike rose thousands of kilometers above the surface, towering higher than any mountain on Earth, glowing with the heat of the impacts. The violence of the event stunned scientists. The comet's fragments, traveling at blistering speeds, unleashed more energy with each strike than any weapon humanity has ever built. One of the impacts alone produced a blast so enormous that its heat and size dwarfed Earth's entire nuclear arsenal. And it didn't happen once. It happened over 20 times in less than a week, each collision carving a fresh wound into the gas giant's swirling atmosphere. But beyond the drama, the collision became one of the most scientifically valuable moments in modern astronomy. From the spread of debris and the shock waves rippling through the clouds, researchers gained rare insight into the composition of Jupiter's upper layers. Traces of elements and molecules hidden deep within the planet were thrust upward, giving us a temporary window into what lies beneath its swirling exterior. What the event revealed went beyond the mechanics of a single planet. It reminded us that the solar system is not a calm, clockwork machine, but a dynamic and sometimes violent place. It showed us that planetary impacts are not just relics of the distant past, but can still happen today. And it shifted our understanding of the role Jupiter may play in shielding Earth from similar fates. As the last plume faded and the scars began to shrink, a quiet realization lingered. We had seen something ancient and powerful, something usually hidden by the slow rhythms of time. And for once, we had not just read about it, we had watched the sky erupt. Stardust and deep impact, cracking open the secrets of a comet. For years, comets were studied from a distance, photographed as they streaked across the sky, observed as they whipped around the sun and vanished again into darkness. But in the early 2000s, something shifted. Scientists began to wonder, what if we could go beyond watching? What if we could physically reach out, not just to see a comet, but to touch it, to bring back a piece of it, or even break one open and see what's inside? That bold idea gave birth to two of NASA's most daring missions, Stardust and Deep Impact. While they were separate endeavors, they were bound by a common goal: to understand comets not as symbols of mystery, but as archives of our solar system's ancient history. Stardust set out to do something that had never been done before. It was launched to intercept a comet called Wild 2, a relatively quiet visitor from the outer solar system. But Stardust wasn't going to land or fly past just to snap pictures. It was going to collect particles, tiny grains of dust streaming off the comet's coma, and bring them back to Earth. That idea alone was ambitious, but the real challenge was how to do it without destroying the delicate samples during collection. The solution came in the form of an extraordinary material called aerogel. So light, it was mostly air, yet strong enough to catch high-speed particles without tearing them apart. The mission was a success. Stardust's delicate collector tray captured thousands of microscopic particles, and in 2006, those precious grains returned home, sealed inside a capsule that landed softly in the Utah desert. What they revealed was astonishing. Among them were signs of unexpected heat, crystals formed at high temperatures, far from the frigid zone where comets are born. If Stardust was the quiet collector, Deep Impact was the cosmic hammer. Its goal was direct and dramatic: smash into a comet and see what came out. The comet wasn't solid like rock or ice. It was soft, porous, almost like a loosely held pile of powder. Inside that powder were traces of complex chemistry, organic compounds, and fine dust that spoke to the comet's ancient past. What no one knew then was that these two missions, Stardust and Deep Impact, would eventually come together in a full-circle moment. Years after Deep Impact's blast, Stardust, having completed its own primary mission, was repurposed to fly by Temple 1 and photograph the crater left behind. And it did. On Valentine's Day 2011, Stardust passed the comet again, this time capturing the scar of that bold impact. A reminder that even in the vacuum of space, human curiosity leaves a mark. These missions didn't just collect data. They changed our relationship with comets, from passive observers to active explorers. And in doing so, they brought us one step closer to understanding not just what comets are made of, but where we come from. Rosetta and Philae, a daring landing on a drifting world. For decades, we had watched comets from afar. We had captured their light, flown past their icy cores, even slammed into one just to see what would happen. But there was one frontier we had never crossed, landing on a comet. That changed with Rosetta. In March of 2004, the European Space Agency launched the most daring comet mission humanity had ever attempted. Rosetta was not just another spacecraft flying through the solar system. It was designed to orbit a comet, study it up close for years, and drop a lander onto its surface. It was, quite literally, a plan to touch an ancient relic drifting through space. The journey would take 10 long years, requiring Rosetta to loop around the inner planets to build up enough speed to chase down its distant target. A strange, peanut-shaped comet named 67P Churyumov-Gerasimenko. During that decade, the spacecraft would swing past Earth and Mars, using their gravity like slingshots, and even visit a couple of asteroids along the way. It was a mission filled with patience, precision, and persistence. The comet didn't look like a ball of ice. It looked like a jagged alien sculpture. With two lobes connected by a narrow bridge of material, it resembled a rubber duck in space. Its surface was dark and rough, pitted with cliffs, canyons, and deep shadows. This wasn't going to be an easy place to land. But ESA was ready. They had built a small lander called Philae, tucked aboard Rosetta like a passenger waiting for their stop. Philae's mission was bold: to descend onto the comet and conduct experiments from the surface. For 2 long hours, the lander tumbled across the landscape, finally coming to rest in a shaded crevice, far from its intended landing site. What followed was a race against time. ESA engineers and scientists scrambled to gather every bit of data they could before the lander fell silent. And remarkably, even from its awkward position, Philae began to speak. It sent back images of the surface, a dark and gritty world littered with ancient dust. Its sensors reported that the ground was harder than expected, more solid than the fluffy, snow-like terrain some scientists had predicted. And then, just as quickly as it had arrived, Philae went quiet. Its battery drained. The lander shut down. But that wasn't the end of its story. As the comet continued its slow orbit toward the sun, sunlight began to reach deeper into the shadows. In June 2015, Philae stirred. A brief transmission reached Earth, just enough to say, "I'm still here." It managed to send back one last burst of data before the growing heat from the sun made the comet too dangerous for Rosetta to stay close. Rosetta captured dramatic scenes: jets of gas erupting from the surface, dust particles drifting off into space, and entire cliffs collapsing as the comet reshaped itself in real time. Rosetta also made one discovery that struck at a long-standing question in planetary science. Where did Earth's water come from? For years, some scientists believed that comets delivered water to our planet in its early days. Still, even if comets weren't our source of water, they might have played a different, equally profound role. The dust and ice blasted from 67P's surface were rich in organic molecules, the essential ingredients for life. Maybe comets didn't give Earth its water, but maybe they gave us something even more precious. As the comet journeyed back into the cold reaches of space, Rosetta began to run out of power. Its solar panels, designed to work near the sun, could no longer provide enough energy to keep the mission alive. So ESA made one last poetic decision. They would end the mission where it began, on the comet itself. Together, Rosetta and Philae did something no one had ever done. They didn't just visit a comet. They lived with it, listened to it, and became part of its story. They brought us closer than we ever thought possible to one of the oldest, most mysterious objects in the solar system. And in doing so, they reminded us that even the most distant, drifting rocks in space can tell us something about where we come from and where we might be going. After decades of exploration, after missions like Giotto, Deep Impact, Stardust, Rosetta, and others, we've begun to assemble a clearer picture. Comets are ancient. They were born in the earliest days of the solar system, long before Earth took shape. They are icy time capsules, locked away in deep cold for billions of years, preserving chemistry that has long since vanished from the inner planets. They are messengers, carrying traces of water, carbon, and even amino acids, the raw ingredients for life as we know it. But even now, many of the old questions remain open. We know that some comets are darker than coal, hiding their bright hearts under layers of carbon dust. We know that their surfaces are fragile, their interiors hollow and porous, held together by the gentlest of gravity. We know that their tails stretch for millions of kilometers, shaped not just by sunlight, but by invisible winds from the sun, turning them into celestial canvases painted with ionized gas and drifting ice. And yet, we still don't know exactly how these icy wanderers were formed. We remain humbled by how little we truly understand. And what's even more remarkable is that much of what we've discovered didn't come from massive spacecraft or billion-dollar observatories. It came from grit, from human determination, from teams of scientists, engineers, dreamers, and storytellers who dared to aim at a moving target millions of kilometers away and say, "Let's go there." Space agencies and private companies alike are looking to the outer solar system, to the Kuiper Belt, to the Oort cloud, where trillions of comets may still lie waiting. We've only scratched the surface, and yet we're already beginning to see how vast and varied this story truly is. But this isn't just a story about science. It's a story about wonder. Because comets still surprise us, they still leave us breathless. A single streak of light across the sky can remind us of how small we are, and yet how far we've come. These ancient travelers, once feared as omens, have become our companions in a cosmic dance. And with each mission, we don't just learn more about them, we learn more about ourselves. We are explorers, always have been, always will be. So the next time you find yourself beneath a clear night sky and you see a comet blazing silently across the stars, remember, that is no stranger. That is an old friend. One we've touched, one we've studied, one we've ridden through the void. It is a messenger from the past, still carrying questions for the future. And if you look closely, if you follow the tale, if you trace the light, you may just see the reflection of us. Curious, fearless, reaching out into the dark and bringing the universe a little closer to home. Thank you for watching. If you enjoyed the content, don't forget to like and subscribe to support me.